Today I will present the solution to Chinese National Olympiad 2019 Problem 5. Firstly, we'll take a look at the problem statement. Given any positive integer c, denote p of c as the largest prime factor of c. The sequence an of positive integers satisfies a1 greater than 1, and an plus 1 is equal to an plus p of an for all n greater than or equal to 1. Prove that there must exist at least one perfect square in sequence an. To get a good understanding of how this function works, we're going to take an approach which is in general really nice for Olympiad problems. We're going to plug in different values for a1. So if a1 is equal to 7, for instance, then the sequence goes like this. The largest prime divisor of 7 is 7 itself, therefore we get 14, and 7 stays the largest prime divisor. So the sequence continues just by increasing by 7. Now we have 42, which leads to 49. And this is already a perfect square. So yeah, of course the sequence continues, but I'm going to stop here because we want to find out that all such sequences contain a square, and for the sequence beginning with 7 we are already done at this point. So another example would be this one where a1 is equal to 12. Therefore, because 3 is the largest prime divisor of 12, we get 12 leads to 15, then 5 is the largest prime divisor, 5 again, and 25. So yeah, we are done again in this case. We note that in both cases, whenever ak has a really large prime divisor, we continue in steps of p of an, ak, and this largest prime divisor does not stop in the following iterations until we hit the value of p squared. For instance, here at this point we have p equals to 7, which is the largest prime divisor of 7 and compared to 7 really large, in fact with ratio 1. And at this point we have p of 15 equal to 5, which is also pretty large in comparison to 15, and therefore we continue by adding 5 until we hit the value p of 15 squared. So yeah, we observe this behavior in both of these functions. Here we are adding 7 with each iteration because it is a really large prime divisor of all of these sequence members. Okay, so we might suspect that this behavior works in general, and from this we're going to formulate a claim, and I'm going to do that right now. Okay, so what we claim is that if p of an is comparatively large in comparison to an, so in particular this is the exact condition we want to be true, then for all n less than or equal to k less than or equal to n, we have p of ak is equal to p of an, but I'm going to have to define what n means. So where n is maximal such that an is less than or equal to p of an squared. This is already a nice claim, but I'm going to amend it by an addition. So moreover, an is exactly equal to p of an squared. This is really nice because am is a member of the sequence am, and am is equal to p of an squared. If we manage to prove that, we are done in this case, because p of an squared is a square and a member of our sequence. Now continue with the proof. The first part of this claim can be proven by induction, because we see that p of ak must also divide ak plus 1. So let's set up an induction. Our hypothesis is that for some n less than or equal to k less than n, we already have p of ak is equal to p of an. Okay? So then, by what I've just said, we note that p of an, which is equal to p of ak, divides ak by definition, and thus it also divides ak plus p of ak, which equals ak plus 1 exactly. Okay, so we know that if this holds true, then p of an also divides ak plus 1, but ak plus 1 divided by p of an is less than or equal to p of an squared over p of an, because ak plus 1 is less than or equal to am for k less than m, and am is less than or equal to p of an squared. This is equal to p of an. So any other prime divisors of ak plus 1, which are not p of an, ak plus 1, which is equal to p of an, are also prime divisors of this number. But this quantity is less than or equal to p of an, and thus no prime larger than p of an, can divide this quantity, and thus the largest prime divisor of ak plus 1 is equal to p of an. Very nice. So we are finished with the first part of our claim. Now to the last part. We can, by the first part, we already know that p of am is equal to p of an, and thus p of an must divide am. In addition, we consider the definition of m, which tells us that am is less than or equal to p of an squared, which is less than am plus 1, because otherwise m would not be maximal. So this is less than or equal to am plus p of an, or p of an. And this inequality, am is less than or equal to p of an squared, is less than am plus p of an, combined with this divisibility fact, proves that am is equal to p of an squared. So we are done with proving our claim. So what this claim told us is that it is enough to find some n such that p of an squared is greater than or equal than an. Because in this case we will find another integer, or possibly another integer m, such that am is exactly equal to p of an squared, which is a square, and then we are done. So what we're going to do in the second part of our proof is to try to find some, or to rather than that, to try to prove that there's always an integer n such that p of an squared is greater than or equal to an. Okay, so one possible idea for solving this modified problem is to consider a new sequence. In particular, we're going to, or we could consider the sequence an over p of an squared. This is a possible idea, which is not bad, because sometimes it increases, because if this p stays constant and an is a strictly increasing function, then this quantity will grow, but it could decrease dramatically if p of an just increases with an iteration, and so on. So if we manage to show that sometimes this sequence has terms less than 1 or less than or equal to 1, we are done. But what is not good about this approach is that we can't really tell when jumps in p of an are going to happen, which is required to prove that at some point it's going to sink below the value of 1. So a new idea, which is actually going to be the final idea to prove our statement, is to consider two sequences and their behavior and compare them, which are an divided by p of an and p of an itself. We can practically do the same thing, but we don't want to show that any sequence decreases below 1 at any point, but rather we want to show that at some point p of an is larger than or equal to an over p of an. This is good because, first of all, both are integer sequences, so they are not hard to deal with. Okay, so examine this sequence, which I've already said is quite interesting. So we consider how it changes. We consider the value an plus 1 divided by p of an plus 1. This is nothing but an plus p of an divided by p of an plus 1. And at this point we see that it might be a good idea to use some bounding between p of an plus 1 and p of an. We can do that because we know that p of an divides an plus 1, which implies p of an is less than or equal to p of an plus 1. So it is a good idea to use this fact right now, because then these are going to cancel out and we're going to get a really nice result, which is that this is less than or equal to an plus p of an divided by p of an, or an divided by p of an, which is the prior term in the sequence, plus 1. Really nice. So this basically tells us that that sequence can only increase by at most 1 within one iteration. But we also know that it is an integer sequence. So this is really nice behavior. This tells us that if an divided by p of an grows without bound, so I'm going to write it down, if an divided by p of an is unbounded from above, then it will take all integer values larger than or equal to its first instance. Because it can only increase by at most 1 in each iteration. Now we are practically done in this case by the following argument. There are infinitely many primes. Therefore, there is also some prime larger than this value, however large it might be. So if an divided by p of an takes all integer values greater than or equal to that, then it will also sometimes be a prime. And as I've already said, this is, or mentioned before, this is really good. So exists q prime and an integer such that q is equal to an divided by p of an. So because of the definition of p of an and because q is also a prime divisor of an, it follows immediately that p of an is greater than or equal to q. But q is nothing but an divided by p of an, which is exactly what we wanted. P of an is greater than or equal to an divided by p of an, and by the claim we are done in this case. What we need to do to finish with our proof is to consider the second case, where the sequence an divided by p of an is bounded from above. So let there be an integer big N such that for all indices small n in n, an divided by p of an is less than n. Intuitively, it should make sense that this case is not hard to deal with. After all, as n goes to infinity, an also grows without bound because it is a strictly increasing integer function. This means, in order to make this inequality true, p of an must also grow to infinity in a linear fashion with respect to an. So there's some constant factor, namely 1 over n, such that p of an grows larger than 1 over n big N times an. So if we just choose an large enough, then obviously p of an squared must be larger than or equal to an, no matter how big this constant n is. So we can formalize this intuitive reasoning to come up with the proof. So we choose n such that an is greater than capital N squared. Therefore, we know p of an is greater than an divided by n. And keep in mind, I'm just doing some algebraic manipulation to finish the proof, but there are probably other ways, and this is not the hard part. You have to come up with the intuitive reasoning and then finish the proof. So basically, this is also greater than n because an is greater than n squared. Furthermore, this is again greater than an over p of an. This is exactly the relation we wanted. Therefore, in any case, we can show that there exists an index n such that p of an is greater than or equal to an divided by p of an. Therefore, we can plug in this value for n in our claim from previously, which yields us another index n such that an is equal to p of an squared. And therefore, we are done.